There is something physicists stopped saying out loud around the turn of the century. They stopped asking, what is the universe made of? And they started asking something far stranger. What shape is it? That shift, quiet, technical, almost invisible to the public, turned out to be one of the most radical moves in the history of science. Because when you stop asking about substance and start asking about structure, you are no longer doing the same kind of physics. You are doing something closer to architecture, something closer to geometry, something that looks, from a certain angle, almost like philosophy. This is File 017. The archive designation is Reality Architecture. What follows is a reconstruction of how 21st century physics became, quietly and almost without announcement, a science of shape. Let's start with what everyone agreed on. By the late 20th century, physics had two towering frameworks: general relativity, Einstein's description of gravity as the curvature of space-time, and quantum mechanics, the probabilistic rulebook for particles and fields at the smallest scales. Both were tested. Both worked. Both were, by any reasonable measure, correct. The problem was simple and devastating. They could not both be right at the same time, not because the math was wrong, because the geometry was wrong. General relativity assumes a smooth, continuous space-time, a fabric that bends and curves. Quantum mechanics assumes a world that is fundamentally grainy, probabilistic, non-continuous. These two pictures of geometry are not compatible, and every physicist in the late 20th century knew it. What they did next is where the story gets strange. Instead of abandoning geometry, instead of saying, perhaps the universe is not fundamentally geometric at all, they doubled down. They pushed geometry further. They asked, what if the geometry we assumed was simply too small, too ordinary? What if the universe has dimensions we cannot perceive, shapes we cannot visualize, curvatures operating at scales we have never been able to probe? This was not a retreat. This was an escalation. String theory arrived first. And whatever you think of its current status, its core move was geometric. The fundamental objects were not point particles. They were one-dimensional strings, vibrating in 10 or 11 dimensions. The different particles we observe, electrons, quarks, photons, were not different substances. They were different vibrational modes of the same geometric object, different frequencies of the same shape. The universe, in this picture, was not made of things. It was made of vibrations in a high-dimensional geometric space. The archive flags this moment because most public accounts of string theory focus on the strings, the vibrations, the extra dimensions as exotic curiosities. What the archive shows is that the deeper shift was elsewhere. It was in the realization that geometry itself was doing the physical work. Mass was not a property of matter. It was a geometric frequency. Force was not transmitted by particles. It was expressed as curvature. The question was not what particles are made of. The question was, what is the shape of the space they live in? This is where the first fracture appears, because the geometry is doing the physical work. If shape is more fundamental than substance, then the question of which geometry becomes urgent. And in the early 21st century, physicists started finding something uncomfortable. The geometry kept depending on how you looked at it. This was called duality, and it became one of the defining features of theoretical physics after 2000. Two theories, formulated in completely different geometric terms, different numbers of dimensions, different shapes of space, different fundamental objects, turned out to be mathematically equivalent, not approximately equivalent, exactly equivalent. The same physics, described by two irreconcilable geometric pictures. The most famous example is the ADS/CFT correspondence, a theory of gravity in a curved, negatively curved space, anti de Sitter space, turned out to be exactly equivalent to a quantum field theory with no gravity at all, living on the boundary of that space, like a hologram, a three-dimensional physical reality encoded in a two-dimensional surface. Pause here, because this is where the archive signal changes. If two different geometries describe exactly the same physical reality, then neither geometry is the real one. They are both models, both useful, both limited. The universe is not actually the higher dimensional curved space. It is not actually the flat boundary. It is something that can be described by both something that the geometry is pointing toward but not capturing. Geometry, in other words, was a language, a remarkably powerful language, but still a language, and languages have limits. The 21st century did not abandon geometric language. It could not. The tools were too powerful, the results too precise. But the most careful physicists started treating their geometric frameworks differently, not as descriptions of reality, but as computational architectures, ways of organizing calculation so that the answer comes out right, without any claim that the scaffolding is real. This is a subtle distinction, but it is the distinction that matters. Consider what happened with spacetime itself. In general relativity, spacetime is a stage. It is a fundamental geometric structure in which everything else happens. Einstein's great insight was that this stage is not passive. It bends in response to mass and energy, and that bending is what we call gravity. The geometry of spacetime is the physics of gravity. But in the early 21st century, a quiet research program began asking a different question. What if spacetime is not fundamental? What if it is emergent? Emergent means, what if spacetime is not a basic ingredient of reality, but a derived structure, something that arises from something else, the way temperature arises from the motion of molecules, the way wetness arises from the collective behavior of water molecules? What if the smooth, continuous geometric stage of general relativity is a large-scale approximation to something that is not geometric at all at the deepest level? The archive marks this as one of the most significant conceptual moves of the period. Because if space-time is emergent, then the geometry of the universe is not a given. It is a result. And the question shifts from describing the geometry to explaining how the geometry arose in the first place. The tool that physicists reached for was quantum entanglement in the holographic picture. It turned out that the geometric distance between 2 points in the bulk, the higher dimensional space, was related to the degree of quantum entanglement between regions of the boundary theory. Geometry was not prior to quantum mechanics. Geometry was built from quantum entanglement. Space itself was a kind of correlation structure. This was not a metaphor. The mathematics was precise. The connection was quantitative. Space, in this framework, is what entanglement looks like when you zoom out far enough. Now consider what this means for you. Standing in a room, measuring the distance between two walls. That distance, that perfectly ordinary, apparently fundamental geometric fact, is, in this framework, a macroscopic expression of an underlying quantum information structure. The geometry you perceive, the space you navigate, is an emergent pattern in a deeper, non-geometric substrate. The room you are in right now is a large-scale approximation, a very good one, but an approximation. The archive does not say this is proven. The archive says this is where the most serious theoretical work was pointing. The models were incomplete. The framework was under construction, but the direction was clear, and the direction was this. The geometry of the universe is not the bottom of the explanation. It is somewhere in the middle. There is one more layer. In the second decade of the 21st century, a group of physicists and mathematicians began working on a framework called amplituhedron, a geometric object whose volume directly encodes the probabilities of particle interactions. Calculations that required thousands of terms using the standard approach could be performed in a few lines by computing a geometric volume. The striking thing was not the efficiency. The striking thing was what the geometry discarded. The amplituhedron formulation did not use space-time. It did not use locality, the assumption that things only interact when they are close together. It did not use unitarity in the traditional sense. It produced correct physical predictions by computing properties of a geometric shape in an abstract mathematical space, with no reference to the physical space where the particles supposedly lived. The framework was working. The space-time was optional. This is a signal the archive keeps returning to. Not that space-time is wrong. Not that geometry is an illusion, but that the geometric frameworks physicists use, however powerful, however precise, are instruments of calculation whose relationship to the actual structure of reality remains genuinely, rigorously, productively open. The obsession with geometry in 21st century physics was not a mistake. It was extraordinarily fruitful. But the most honest reading of where it led is not a map of the universe. It is a set of increasingly precise questions about whether any map is possible. What the 21st century bequeathed was not a final geometric picture of reality. It bequeathed a much more interesting problem. A collection of geometric frameworks, each internally consistent, each producing accurate predictions, none of them obviously more fundamental than the others, and all of them pointing, from different angles in different languages, towards something that the geometry keeps describing but never quite reaching. The shape of the universe is not a fact waiting to be uncovered. It is a question that keeps changing its form every time you find a better tool to ask it with. That, from the archive's position, is not a failure of 21st century physics. It is its most important result. Signal stable. Archive updated. Transmission paused.